So today we're gonna start a new chapter, chapter 9, and it is about trees. So trees are important graphs. This is a very simple but useful class of graphs. So first, let's talk about the definition and basic properties. Introduction to the tree. So what is a tree? A tree is a graph like this, like a tree. It's like if you walk on campus, you will see trees like this, right? Trees are things like that. So it is really a graph that looks like a real tree. And that's not a very precise definition for mathematics. So let me give you a precise definition. So a tree is a simple graph, so we don't have any multiple edges or loops. Let's say T, V, comma, E, such that for any U and V in our vertex set V, there is a unique simple path from U to V. What does that mean? The simple path means it's a path that has no repeated vertices. So for instance, here in this graph, this is a tree because if you take any two vertices, maybe this and this, you can find a unique path from here to there. Simple path without visiting a vertex more than once. So like this, you can see there's a unique simple path. For any two vertices like this and this, you can find, you can follow these edges and then get there. And this is the only way to get from this vertex to this vertex without visiting one vertex more than once. Okay? So it is a simple, it is a tree. So let me give you a more example. So yeah, maybe I already gave you, this is a tree, maybe, but this is not a tree, because if you take U and V here and here, there are more than one simple path. You can go this way, or you can go in this way, or this way. There are two different simple paths from one vertex U to another vertex V. This is not a tree. Not a tree. And what about this? Let's say. So this is a whole graph. G is this. This is not a tree, because tree must be connected. Because if you take one U and V like this, there is no simple path from U to V. So it's not tree. It's not a tree. But this one is tree. Okay? The tree must be connected, because connected graph means if you have two vertices, U and V, there is always a path from connecting these two points. Okay. And a tree, we say that sometimes it's useful to specify one vertex in a tree, and we call it root. A root. So in this case, we say it's a rooted tree. A rooted tree is a tree with a special vertex. It's called root. So it's like this. Let's say we have 1, 2, 3, 4, 5, 6, 7, things like that. And I'm going to specify this so that it's a root. So 3 is a root. Then we say that it's a rooted tree with root 3. Okay. Rooted tree, so think of this as really a tree where this is on the ground, you know, so it's a root. It grows like that, right? So imagine something like that. But yeah, if you just choose one vertex and say there's a root, that is a rooted tree. So it's a rooted tree with, say, root 3. Okay. The rooted trees are useful in organizing many things. It can be used in a database. So file directory. If you have your computer, you may have something like my computer. And in your computer, you have like a my document. And maybe you have desktop. And in your document, you may have some things like that, report or homework. In your desktop, you have something, I don't know. So this is a tree structure. And maybe you can say, okay, this is a root, it's a rooted tree, if you say this is a root. Okay. The tree is the simplest. We will learn more characterizations of trees. So the definition of a tree so far is a graph where whenever you take two vertices, there is a unique simple path between them. But there are equivalent definitions of trees. We will learn them later. Something like so trees are connected graph, but it's the simplest possible connected graph in some sense. And also trees don't have any cycles, because if you have a cycle, there are two different paths from one vertex to another, right? You can go this way or this way. So it does not have cycle. Those graphs are called acyclic graph, and trees are also simplest acyclic graph. Maybe not, largest acyclic graph, I should say. But we will get back to that topic later. Okay, so an application of trees is this. Huffman code. So in order to store something in computer, we need to change that into like bits, zeros and ones, binary string. So in order to give input, because computers can only understand the bit strings, we need to change like data into bit strings, 0, 1 string. So for instance, alphabet, we use alphabet, we know A, B, C, D, but if you want to give these input to a computer, so let us like A, B, C, D, E, and code, we say that code. We need to encode this in terms of zeros and ones. Suppose that we have only 5 letters to encode. So 1, 0, 0, 0, 0, 0, 1, 0, 1, like binary numbers. This is fine. We can just. Oh, no. This is not a good thing, right? So I just say that, okay, this is first letter, so it's 0, 1, 2, 3, 4 in binary numbers, right? This is fine. So suppose that you want to encode the word like a bed. Then you can write this as like So B, what is B in binary code that we have over here? 001 A, 000. What about D? 010. Oh no, 011. And computer can understand this because the computer knows the correspondence or this table. So if by looking at this 001, computer can understand this as B. And this, what is this? This is A, and this 011 is D. So you can recover this. This is one-to-one correspondence. I mean, if you have a code like this, which is, if it's correct, it's made correctly like this, then you can recover this is B, this is A, and this is D. Okay? So far, nothing's bad, but we want to be more efficient. Because alphabet, there are many alphabets out there, but some letters occur more frequently than the other. For instance, alphabet E occurs much more frequently than letters like Q or X, Z, right? So the idea is, if some letters occur more often, then we want to give it a shorter length, because if the length is, because we want to make the code as short as possible, right, in general. So for instance, suppose that we just use this and then try to, okay, maybe I can, suppose that I'm just giving you just A, B, E, D, C, A. Suppose that I'm just writing just random sequence of alphabet. Suppose that we have to encode this. You can use the same thing, A like 000, B 001, etc. So assign string of length 3 to each letter, then it's fine, you can just encode this. But that's not going to be very efficient. So if you assign in a slightly different way, so because you can see A occurs many times, 1, 2, 3, 4, 5, like a 7. So maybe if we assign just very short string to A, maybe it can be more efficient. So assign like, say 0 to A. And what about B? B. So for A, B, oh no. So it's like, okay, let me write this way. So for A, we say 0. Okay, A is going to be 0. And B, I'm going to write this way. I'm going to change this. I'm not going to find the best possible way. Just find something that's more efficient than this. So okay, if you use this coding system, this will be represented by what? A's, so we have 1, 2, 3, 4, 5, 6 zeros. And then what is B? 1, 0, 0. What is E? 1, 1, 1. What is C? 1, 0, 1. A, 0. Okay? Right. And if you know this table and this sequence of zeros and ones, then you can recover these letters, right? Because notice that, so coding system, the assignment of these letters must be in such a way that we can really recover the original letters. Otherwise, it's useless, right? But in this case, you can see that if you use this coding system, you can recover the letters always. Because A is the only letter starting with 0. Others, they start with 1s, and then after 1, you know, they have the same length. So for instance, here, it is 0, so it must be A. It must be all A's, right? And here it begins with 1, so it's something else, not A. And we know that these all have length 3, so we can cut this into 3 things, and like this. Okay. And then you know these are all A and B and E and C and A. You can recover. And this is shorter than the code if you use the previous table, right? If something occurs more frequently, assign a short string to it. That's the idea, basically. And Huffman code is a way to do this. So algorithm, here is an algorithm to create optimal Huffman code. Huffman code is coding system, so assigning letters, assigning bit strings to letters. So you are not just given, so the situation is this, you are not just given letters A, B, C, D, etc. If you don't have any information about just A, B, C, D, then you don't know which alphabet occurs more frequently or not. So we need to know not just the letters to encode, but also the frequencies of them. So that you will be given this as an input. The input is a table of, say, n letters and their frequencies. Say F1. So let's say the frequencies are given in this increasing order. So for instance, alphabet A occurs like, the frequency of A is like 120 and B is 72, something like that. They are given. And output, this algorithm will produce this output, which is an optimal Huffman code. So what is this? I haven't defined this yet. But the Huffman code is as a tree. I'm going to explain this as an example. So it will produce some tree, and the tree will determine how we encode these letters. Okay, maybe I can just give you an example first. Okay, let me give you an example first. I'll get back to this later. The Huffman code, the coding system example. So it's a tree, basically, binary tree. And so this is the root. Root is at the top. And these are called leaves, the terminal vertices. You go down, if you start with a root, with a vertex called root, and then you can go either, it may have two branches or nothing. If there's nothing below, they are called leaves. And for these leaves, we assign alphabet. So let's say A, B, C, D, E. Then this gives us a table. So the letter and bit string, the table is like this. So A, B, C, D, E. And here we have left side and right side. For every left edge, write down 1. So it's 1, 1, 1. So basically 1 and 0. Assign 1 and 0 to each edges. 1, 0, 1, 0. Okay? So here we have a rooted tree, and we have labels on each edge. And what is the definition of a tree? Every two, if you take any two vertices, there is a unique path from one vertex to another. So the bit string assigned to A is the string that you can get by traveling from the root to that vertex. So for instance, A, this is the path, unique path, so it is 1. What about B? You can travel from the root to B in this way, this and this and this. and then you just write down the labels that are on the edge. So 0, 1, 1. What about C? 0, 1, 0, 1. And D, 0, 1, 0, 0. 0, 0 for E. So this is the code. So this is a Huffman code. Optimal means we assign a small string of smaller length to a letter with a large frequency. Okay. Let me explain that algorithm again in the previous page. So I'm going to create a tree like this so that it really is optimal. So the algorithm is quite simple. So here we are given a table of n letters and frequencies, and we want to create a tree where we have the n letters are at the attached at the leaves. So if this algorithm is as follows: if there are two vertices, then it's just nothing. There is nothing difficult. Just create a tree like this where F1, F2. So I'm used to write down the frequencies. So it means you can just put any the letter with frequency F1 here and put the letter with frequency F2 there. So in this case, it's very simple. And if n is greater than or equal to 3, we are going to define this recursively. Find the Huffman code or Huffman tree for. So here we have n frequencies, right? F1, F2, dot, dot, dot. Just add the two smallest numbers, frequencies. So F1 plus F2, F3, F4, the remainings are the same. We have how many? Now n minus 1 frequencies, right? And so we will get a tree with n minus 1 leaves. And there is a change. So, there is a leaf with frequency F1 plus F2, and change that into this, F1, F2. And that's the algorithm. Okay, so recursive, it's rather simple recursive. It's best to describe using an example, of course. So example, so we are given this table, letter and frequencies, A, B, C, D, E. Frequencies are like 2, 3, 7, 8, 12. So we want to find a tree with frequencies like 2, 3, 7, 8, 12, right? We want to create a tree with frequencies this. But because we have more than 2, we will merge these two together. So if you add this, you get 5, 7, 8, 12. So we will first find the Huffman tree for this, for these frequencies. But again, we have more than 2, so merge the two smallest ones. So 12. If you add these two together, we get 12, right? And then that will be 8 and 12, 12. We have 2 12s. It's fine that we have more, the same numbers twice or more. And here, we add two smallest numbers together, then we get 12 and, right? Now we have just two frequencies. Now we can create the Huffman tree for this. The Huffman tree for this is just this, right? So we begin with this. But now, you notice that 20 was obtained by adding 8 and 12, right? So we are going to split this into 2 branches. So here, we're going backward, like here is going to be 8 and 12. It doesn't matter which side you put 12 or 20. They'll be, that's fine. And what else? Now this is the Huffman tree for this 2 frequencies. This is an optimal Huffman code for this. So for this we have to change this a little bit. So 12 is sum of these 2. You can, it's fine which one you take. Let's say this. And this, split this into 5 and 7, 8 and 12. Okay? So this is an optimal code for this. And finally, we know that 5 was obtained by adding 2 and 3. So we split this into 2. So the Huffman tree will be this. So 2, 3, 7, 8, 12. So what is the code then? Huffman code then? Letter, maybe I can write over here. So it's a string. We assign ones over here, 1, 1, 1, 1, and zeros for the left, right edges, right? So A is the letter with frequency 2, right? And if you follow the tree from the root to 2, then you get 1, 1, 1. So it's going to be 1, 1, 1. All right? What about 3? B, it has frequency 3, so it's 0, 0, 1, 1, 0. 1. And 7, 0, 1, 0. 8, 0, 1. 12, 0, 0. You can see if the frequencies get larger, then you can see the length of the string gets smaller, right? So yeah, it's a good coding system. And if you know this, then you can always recover the letter. This is good coding system, really. If you give the strings just randomly, then that's not going to be a good code. You may not be able to recover the letters if you are given just a string. So for instance, yeah, maybe you can get some, I didn't write that down over here, but right. Let's see if we can really do this. So using that coding system, let me write the code again. But string, the tree, 2, 3, 7, 8, 12, right? 1, 1, 1, 0, 0, 0, 1, 0. So this is A, B, is it A, B, C, D, E? I think so, right? Oh yeah, we don't need this anymore, by the way. Okay. So the letters, the frequencies we don't need. So this is the Huffman code that we got. So let's say we have like ACE. What is this? So A is 1, 1, 1. What is C? 1, 0. What is E? 0, 0, right? Suppose that now we don't know what these letters were. And from this, how can we recover the letters? You just follow the tree, right? From here, 1, 1, 1, just follow. It is 1, so we use 1, like this. And then another 1 here, and then 1 and here. Now we are at the end, so this means this is going to be A. Now what? Here is 1. We are not yet at any leaf, so we continue. 0. Now we are at our leaf, and the label is C, so it's going to be C. And what about this? 0 and 0 is E. So we can recover like that. There is no ambiguity here. But if the coding system is, if you didn't pay much attention when you create a coding system, that may not be, there may be some ambiguity. For instance, a simplest example, suppose that we have just ABC, and suppose that, okay, AB occurs very often, so I'm going to put 0 for A and 1 for B, and then 0, 1 for C. This one, then, suppose that you are given 0, 1, 1, then you cannot really determine what a letter corresponds to this. There's no unique way to create this, because it could be ABB also represented by this, but C, if you say this is C and B, this also is represented by this. So in this case, this is a useless coding system. You cannot use this as a code. But Huffman code is a good one, and it's optimal. Okay. Do you think this kind of coding system is useful? I think you should agree, because you are using coding system yourself, right? Like, by shortening the words, like, I don't know, like 학식 in Korean, This is a coding system. You just shorten the word, but you have to make this clear so that it really represents what you meant. But anyway, coding system is very useful, and it's everywhere, basically. All right, 9.2, the next section, terminology and characterization of trees. The definition of a tree, I told you, but there are equivalent definitions. First, let me give you a bunch of terminologies. T is a tree with rooted tree. So let me give you it's like that. It's kind of interesting because I didn't really look at my lecture note, and I thought I drew this randomly, but it happened that same drawing as the thing in my lecture note. Okay, let me put some more dots. All right, so V0, consider a simple path, V0, V1, V2, Vn, Vn minus 1, etc. There could be more. So V0, V1, Vn. Oh, it should be Vn minus 1 over the top. Simple path. Let's say V0, not R0. Okay. Vn is called a child of Vn minus 1. Of course, Vn minus 1 is a child of Vn minus 2, etc. V1 is a child of V0. Think of this as a family tree that represents your family. And Vn minus 1 is called the parent of Vn. So this is a child and this is the parent. And these things that are above V0, so V0 or Vn, I mean V1 dot 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 Vn and minus 1, these are called ancestors of Vn. So these are ancestors. So parent is also an ancestor. And parent is an ancestor. Parents, etc. These are all ancestors. And if X is an ancestor of Y, we say that Y is a descendant of, it should be A, descendant of X. Right? So in this case, Vn is a descendant of V1 or V2. Vn is a descendant of V0, etc. Okay. And if X, Y are children of Z, then we say that, so if they have the same, in other words, X, Y, they have the same parent, then we say that X and Y are siblings. They are called siblings. If X has no children, then we say that X is a terminal vertex or leaf or leaf. Actually, it's a tree. Think of this as a tree upside down. So this is a root. So this is the ground, and this at the top is going to be a leaf, right? So that's why it's called a leaf. The terminal vertex or leaf. Oh yeah, I need more space. So there are many definitions here, but there are somehow things that we use in our real life. Like it's similar to our language, so it should be not that difficult to remember. So if X is not a terminal vertex, then we say that X is an internal vertex. In other words, every vertex is either a terminal vertex or an internal vertex. So root, for instance, is an internal vertex if there is more edges. If there's only just one dot, that's a tree. That can be a rooted tree. In that case, a root is a terminal vertex. Okay. So in our example, so these are terminal vertices, right? Or leaves, and other vertices are internal vertices. The subtree of no, this is strange. Okay, all right, this is the definition. The subtree of T, so T is the original tree, rooted at X, X is one vertex in T, is the graph, say V comma E, where, what is V? V is X union all descendants of X. And E is what? A set of edges E, where E is an edge. This is a difficult way to explain something that's very simple. You will see what I mean. A simple path from X to some vertex in V. Yeah, in mathematics, this happens quite often. The concept is very simple, but the description is kind of long and like this. The idea is very simple. So subtree, we have a tree. Subtree rooted at, say, here. Subtree rooted at X is just a tree that's below X. This tree is the subtree. Okay? But why did I write that long sentence here? To be very precise. So what does this mean? X, so what is the vertex set? It contains X, of course, and all the descendants. So we have to contain all of this in our vertex set V. What does E mean here? There is a simple path from this to some vertex. Oh, this should be capital V. Some vertex. If there is some vertex V and it's a simple path, there is a simple path, we are going to have all edges there. That means basically you take all the edges. So all descendants and all edges from the tree, original tree. Okay? You don't create no more edges or more vertices. You just take all edges, all vertices from the tree below that vertex X. So this is going to be the new root for this tree. Okay? So sometimes we say it like that. The subtree of T rooted at X. All right. Okay. So trees have many interesting properties, and this is one of them. T, say, is a tree with n vertices, and at least 2. One vertex just itself is also called a tree. It's also considered a tree. Vertex set is just one vertex, no edges. That's also a tree. But we are not going to consider that in this theorem. Then this T has at least 2 vertices of degree 1. Proof. Sometimes a vertex of degree 1 is also called a leaf. But if you remember the many terminologies that are defined here, they are defined on a rooted tree. So leaf is defined only for a rooted tree over here, but sometimes some textbook, a tree, a vertex of degree 1 is also called a leaf. So how can you prove this? The idea is, in other words, here, let me erase this. There are many vertices of degree 1 or leaves. There are at least 2. How can we show this? If there is, the idea is this. If the degree is 1, that's fine. But if the degree is not 1, what does that mean? It's a tree, so it must be connected. The degree should be 1 or 2 or 3, etc., not 0. If the degree is not 1, you can go either way. There should be at least 2 ways from this vertex, right? You can go this or this, right? And here, if the degree is not 1, you can continue, right? You can continue. If the degree is 1, that's fine, but otherwise you can continue. You can keep going like that. But because this is a tree, you cannot go around and then get back, right? Because then we will have 2 different simple paths, right? So the only possibility that you cannot go any further is that this vertex has degree 1. That's the only possibility that you cannot go any further. Otherwise, you can continue. The degree is 2, right? And the graph is finite. You cannot go forever, so you have to stop some point here, and also you have to stop at some point here. That means you have to have vertices of degree 1. That's basically the idea. But I'm going to explain that in sentence. But you can first get the idea like that. Actually, the simplest way to write the proof is this. Find, if you go further and further until you cannot go any further, that means this path is going to be the longest path, right? The length will be the longest. You just take just longest path. Find a longest path. This is a common trick in a simple path, because otherwise you can go like as long as possible. So we have this path. The longest means there are many simple paths, and then the length, you can compute the length of each simple path, and then take a simple path that has the maximum length. Maximum length. There could be more than one such path, but just take one such longest path. And claim is then the degree of u1 and uk must be 1. So these 2 must be 1. Why? Because if degree of u1 is, if not 1, must be greater than 1 or greater than or equal to 2, then we can find a vertex connected to u0 on edge, like a u0, say v, right? Where, of course, v is not different from u1 because this is already counted. Degree 1 must be, but we must have something else, right? But it cannot be one of these. And you cannot, V cannot be one of these. Not just this, U1, U2, all of this, right? Because if V is somewhere here, then we have a simple, two simple paths from this vertex to this vertex, this and this. That's a contradiction to a tree. T is a tree. Otherwise, we have a cycle. Whenever we have a cycle, there are two different paths violating the condition of a tree. That's the reason why this is 1, and also that this is 1. And we just found two vertices different of degree 1. Okay. And that's it. Any question about this proof? right. So let me give you a definition. A graph is called acyclic if it has no cycles. So theorem. So here we have four equivalent definitions for a tree. So let's say T is a graph with n vertices. Let's say simple graphs. Let's consider, because if it's not simple, it's obviously not tree. Then the following are equivalent. First, T is a tree. Or in other words, the definition of a tree. For any UV, there is a unique simple path from U and V, between U and V. This is the definition of a tree that we use, right? The second one, this is also a very common definition. T is connected and acyclic. So connected graph with no cycles. If a graph is connected and it has no cycles, then that's a tree. That's equivalent. And third, T is connected and it has n-1 edges. T is acyclic and it has n-1 edges. So these four, they are all equivalent to each other. All right. So you need to remember them all. So because sometimes you are given only this information. It's connected and you know there's n-1 edges, then you should be able to say immediately that, okay, this is a tree. So this is the minimum number of edges possible to have a connected graph, if you see. Suppose that you have n vertices, 1, 2, 3, 4, 5 vertices. Suppose that the graph is connected. How many edges do you need? At least 4 edges we need. Because, you know, to connect, we have five disconnected components, right, at the beginning. If you add one edge, if you put an edge between two disconnected ones, then you can connect the two things into one. You can merge two things into one. So by adding one edge, you can decrease the number of disconnected components. So at least we have to add 4. For instance, this, and we have 1, 2, 3, 4 components. Maybe this, and this, and this, like that. So 4 is this is the minimum number of edges required to connect n dots. So in other words, this means connected, minimally connected in some sense. Minimally, you can think of this as minimally connected. Connected, but with fewest possible edges. Okay, as few as the number of edges is minimum. What about acyclic? Acyclic and n-1 is the maximum possible number of edges for an acyclic graph. For instance, suppose that we have 1, 2, 3, 4, 5 like that. Of course, if there is no edge, it is of course acyclic, right? Suppose that you add edges so that you have acyclic, right? For instance, what is n here? 1, 2, 3, 4, 5, 6. We have added 1, 2, 3 edges, 4 and 5, right? I added 5 edges, but now you can see if you add one more edge there, you will always get a cycle, like this or this or this. You will always get a cycle. So you cannot add more than n minus 1 edge. So this is the maximum possible number of edges for an acyclic graph. So sometimes in some textbook, it's like, it is written like that. Maybe I didn't write this in the lecture note, but sometimes it's possible to say T is minimally connected. Sometimes it's said like this: T is maximally acyclic. Minimally connected means it is connected, but as long as if you delete one edge, you will always get a disconnected graph. So it's minimally connected. You cannot reduce the number of edges so that it's still connected. Maximally acyclic means it is acyclic right now, but if you add one more edge, then it will not going to be acyclic anymore. But these two are more or less the same as this, because if there are n minus 1 edges, n minus 1 is the smallest number of edges required to have a connected graph. And because n minus 1 edges is the maximum number of edges for an acyclic graph. Okay, so sometimes it's easier to remember. Tree is minimum connected, maximally acyclic. Okay. I cannot prove this everything here, but let me give you a proof of a simple thing. 1 implies 2. So proof. So let's prove 1 implies 2. Basically, we will continue this in the next lecture, but we will proceed in this way. We will prove that 1 implies 2, 2 implies, so it's like cycle, like this implies this, and this implies this implies this, and finally this implies this. We will prove these 4 steps, 4 things. Then that proves that everything is equivalent. So first, 1 implies 2. So 1 means T is a tree, and 2 means it's connected and acyclic. But obviously, clearly T is connected, right? Because the condition for a tree is that for 2 vertices there is a simple path, or unique. If there is a simple path, that means they're connected. So we need to show that it's acyclic. But actually we did this today already. If T has a cycle, consider a simple cycle. Simple cycle means we don't have any, it's possible that it's like that, right? This is also a cycle. But if this, then take this cycle. Maybe the shortest cycle will be a simple cycle. So if there is a cycle, you can always find a simple cycle like that. And then, so let's say this is a simple cycle. Consider U and V. Then obviously we have 2 different simple paths from U and V. Then there are 2 different simple paths from U to V. So it's a contradiction to the tree, contradiction to the assumption of 1. So T is acyclic. Okay? Done last time. So we will do 2 implies 3. If T is connected and acyclic, then it is connected and has n-1 edge. Because it's already connected, we need to show that it has n-1 edges. So induction on n. Actually, if you show some property of a tree, induction is quite useful because tree has a very simple recursive structure. A tree is obtained by adding one dot or one leaf, a vertex of degree 1 to a tree of size 1 less number of vertices. All right, n equals 1, what happens? We have just one dot, that's all. So n-1 edges, because there is no edge. It's clear. We need to show that it has n-1 edges. Suppose that is true for say n, and consider n plus 1. Suppose that it is true for some number n, which is L is 1, and we consider n plus 1. All right, so n plus 1, so we consider a tree with, not tree, T connected acyclic with n plus 1 edges, vertices. T connected and acyclic with n plus 1 edges. Oh, yeah, I keep saying that's edges. I keep mixing edges and vertices. N plus 1 edges. Okay, what happens? Consider, this is a common technique. Consider a longest, because we will find the vertex of degree 1. If you want to find the vertex of degree 1, this is a common technique. Consider a longest simple path in T. So you can obtain such a path by extending a path. You can go as far as possible. But if you at some point you cannot go any further, that means it should be one of the longest. All right, so okay, maybe I don't need a space here. So let's say this is the longest path, like that. Say u0, u1, u say k. The longest is not possible. So you cannot extend any further from both. And we know, because of the condition, degree of u0, degree of uk must be 1. Why? If this is not 1, because it's connected, oh yeah, it's already 1. If it's not 1, the degree it must have at least one edge coming out from this vertex. And because it's longest, you cannot find a new vertex. So that vertex must be one of these. But if you connect this to one of these, you will create a cycle. But the assumption in 2 is that it's acyclic. That means you cannot find any vertex connected to u0 directly by an edge, except to u1. Is that right? If I want, because actually we did this already, but let me repeat. Because if degree of u1 0 equals is greater than 1, there is vertex V such that U0V is also an edge, right? V must be different from U1. Because if this is the only vertex connected to U0 by an edge, the degree must be 1. But our assumption is greater than 1. If V is different from U2, U3, UK, then we can make the path longer, right? By adding V, like this. U0, U1, UK, right? By adding V. This is longer than this. But our assumption is that it's the longest path. Contradiction, right? But if V is one of these, if V is, okay, maybe we can say, if V is Ui for some I, maybe 2 to K, then what happens? Then T has a cycle. But it is acyclic, so it's also a contradiction. Therefore, the degree must be 1. Same for UK. So what's good for a vertex of degree 1? A vertex of degree 1 allows us to make the tree smaller by removing that vertex, right? So let T prime be T minus, say, U0. Just delete one edge, one vertex of degree 1. Then T prime is, what about T prime? Then T prime is what? Is it connected? Yes, it's connected because we deleted a vertex of degree 1, so it's still connected. Is T prime acyclic? Yes. Already in T, we didn't have any cycle. If we delete one vertex, it cannot have any cycle, and acyclic. But what is the number of vertices in T prime? N. And by assumption, by induction hypothesis, T prime has n minus 1 edges, right? Because 3 is true. But what is T? T has one more edge than T has one more edge than T prime, because here we deleted one edge and one vertex. And T has n edges, which is 1 less than the number of vertices of T. So the statement 3 is still true for T. So by induction, it is true for all integers n. And that's the proof that 2 implies 3. By induction, it's true. Is this okay? So for tree, it's a very common technique. Find the vertex of degree 1 and try to remove it to get induction hypothesis or things like that. And now 3 implies 4. So what is 3? Let's go back. Connected n minus 1 edges, then it's acyclic n minus 1 edges. Because n minus edge is the common property, we need to show that it's acyclic, right? Connected n minus 1 edges, then acyclic. That's what we want to show. So basically, we need to show connected n minus 1 edges, then acyclic. This is what we want to show, because n minus 1 edge is right there. So to prove this, just assume that the opposite, T is not acyclic. And then if you can find a contradiction, then it will prove that it should be acyclic. So acyclic, it's not acyclic means it has a cycle. Let's consider a simple cycle. Then T has a simple cycle. Okay? So a cycle like that. Simple cycle. If it's not simple, you can just remove some edges or vertices, and you will get a simple cycle. So let's consider two vertices or adjacent vertices. Consider take one edge, say UV, in the cycle, like this. And let T prime be T except this edge, UV. So keep the vertices, the same vertices, and only remove one edge. So just delete this edge. Like that. That's going to be T prime. Then what happens? T has how many vertices? The same number of vertices, so n vertices. And how many edges are there? Initially, it had n minus 1 edges, but we removed one edge, so it has n minus 2 edges. But is it still connected, T prime? Originally, it was connected, but we deleted one edge. But the edge contained, it was contained in a cycle. So if you delete one edge, the graph should be still connected, because you don't have to use this edge to go from one vertex to another, because you can always go around and still connect it. But this is a contradiction, because for a connected graph with n vertices, we need at least 1 minus 1 edges. If a graph with n vertices is connected, it must have at least n minus 1 edges. Why? Because initially we have just imagine that the n vertices with no edges, and we need to connect all the dots. First, if you add one edge, you can combine two disconnected dots. And if you add one more edge, you can connect two disconnected things. So if you connect all of them, you need at least n minus 1 edges. Like, if there are 4 edges like this, if you want to connect them all, connect this, or this, like that, at least n minus 1 steps are needed. So it's contradiction. Contradiction, because it has n minus 2 edges and still connected. So it's impossible. That means T must be acyclic. That's the proof of this, right? So this implies 3 implies 4. Now, finally, 4 implies 1. Let's go back to the definition or condition. 4 acyclic n minus 1 edges, then it's a tree. Tree means our definition is for every 2 vertices, there is a unique simple path. So T n minus 1 edges has n minus 1 edges and acyclic. Then the unique path. Unique path, let's say. Unique simple path. This is what we want to show. It's tree or tree. So we need to show that there is at least one path, and then we will show that it's unique. So to show that there is at least one path, we need to show that it's connected. So basically the same thing. So suppose that T is not connected, and then try to find the contradiction. So if T is not connected, then what happens? Then it will be, we can imagine this T as a connected component with several things. Let T1, T2, Tk. Here K must be at least 2. This be the connected components. The components of. So T has a bunch of subgraph connected, and they're not connected to each other. And let's say Ni is the number of vertices in Ti, each component. Then T is acyclic, so each component must be acyclic, right? So each Ti is acyclic, right? Because if there is a cycle T1 in T1, yeah, it is a cycle in T too. So, right. 2 implies 2 and 3. Let's go back to 2 and 3. We have consider each component Ti. Ti is connected and acyclic. What does that mean? It must have n-1 edges, where n is the number of vertices. So by 2 n implies 3, by this condition, Ti has how many edges? It has ni vertices, and because it's connected and acyclic, it must have ni-1 edges, right? Because we have 1 less edges than vertices. So then what is the total number of edges? Number of edges in T. It is n-1, of course, right? But it will be the sum of the edges in each component, right? Sum of each component, ni-1, I from 1 to k. Right? But what is this? Sum of ni's, what is that? Number of vertices. And this is just k. Okay? This is a contradiction because k is greater than or equal to 2. It's a contradiction. n-1 cannot be equal to this, because this means k equals 1. It's a contradiction. Therefore, this assumption is wrong, so T is connected. Now we need to show that there is a unique path, a unique simple path, not different two. Now we need to show that, so suppose, another proof by contradiction. Suppose that there are two simple paths different from one vertex u to the different vertex v. We will find a contradiction to the assumption. So here we have u, here we have v. Okay? So here it goes like this, some path, and another simple path, but they may have some they may share some vertices and edges, but eventually it looks like this, right? It goes like this, one path goes like this. Maybe they can separate and then merge, but like that. But here you can see a cycle. This is going to be a cycle. Then we obtain a cycle from this. Contradiction, because we assume that the graph is acyclic. It's a contradiction. Therefore, there is a unique simple path for any vertex u to v. And that's it. There is unique simple path for every 2 vertices. That means it's a tree. Is this okay? All right. Then we can continue. So, yeah, just it's helpful to remember the equivalent definitions: tree, connected acyclic, and connected n-1 edges, cycle, acyclic n-1 edges. And in particular, if T is a tree with n vertices, then the number of edges is n-1. That's a very simple fact, but useful.